Alright guys, if the bell ringer still does not make sense after the simulation, here's a quick video showing you how to go about it. Okay, so we have Hooke's law, which is force equals negative kx. We know that amplitude equals the maximum displacement, so we can say that if we reach the maximum displacement, then Hooke's law equals negative ka. Alright, and I'm just going to go straight for the simulation. Here it is. And the reason why I gave you this one is so we can have two, let me make this a little bigger, two springs, right? We'll pick 50 grams, we'll stop it, and I'm going to assume, just for the sake of this example, that this is the maximum displacement. So I will get the mass right to the line, and then we'll let it oscillate. This is pretty fast, so I'm going to make it slow. Now we're going to drop another mass, so let's say it's double the mass, so 100 grams, right? We'll stop it, and then I'm going to stretch it out to the same distance, right? The same displacement, because that's what it's saying. The example says that when we reach the same amplitude, right, the amplitude, then another mass was added on top of it. So this will help. And then I will release exactly at the same moment when it reaches there. So I think it is very obvious what's happening, right? You guys can clearly see. So now let's see our answer choices. A, the maximum velocity does not change. Well, it is very obvious that it is going slower. B, the amplitude of oscillation decreases. C, the frequency of oscillation, F, does not change. And D, the frequency of oscillations increases. And E, the period of oscillation increases. Okay. So since we have two different springs, that's why it looks like the amplitude is decreased. But that's because we're using the same, two different springs. If we're using the same, the amplitude would remain the same because it was a frictionless surface. So now let's look at frequency and period, right? So we're going to cancel these two. So frequency and period. So period we defined as the time it takes a system, the time a system takes to complete one oscillation, one cycle. And we have the relationship of period and frequency in this way. Period equals 1 divided by the frequency. I'm going to give you another formula for this one, right? This is the period of a system where you have a mass on a spring. It'll be 2 pi times the square root of the mass divided by spring constant. So the period, as you can see, it's not related. Well, I mean, mass is important, right? So something has to change because we're changing the mass. The spring constant is a constant. Pi is pi, 2 is 2. So if we increase the mass, we're going to increase the period, right? And you saw it was going slower. If it's going slower, then the period increases. It takes more time to complete one oscillation, right? So let's say if this is oscillating like that, right? And then we put another mass, so it's harder to move, right? So the period increases. Now, if the period increases, notice how period and frequency are inversely proportional. So if the period increases, that means the frequency has to decrease, right? Don't forget that the frequency is the number of events or cycles per unit time. So if it's taking us more time to do one cycle, then that's going to reduce the number of cycles per unit time, okay? So if we go back to the answer choices, the frequency does change. It decreases. This one says increase, so we cancel A, B, C, D. And the only one left is E. The period of oscillation increases. It takes more time to complete one oscillation. That's it.